Good morning, good afternoon, or good evening. This is Mr. P. How is everybody doing today? It's good to have you here. Today we're going to be doing guided notes for section 12.2, probability, in our secondary math 2 class. So let's talk about the fundamental counting principle. That is, if there's one event that can occur in m ways, and another event can occur in n ways, the number of ways that both can occur is m times n. Perhaps you remember this. It's kind of like if you roll a six-sided die and flip a coin, like we did in our last lesson, you probably noticed that if I have one in a heads, one in a tails, two in a heads, two in a tails, I'm really just doubling each outcome for my six-sided die. Or if you prefer to think of it this way, there's one heads, two heads, three heads. I'm really just multiplying the heads by 6 and then the tails by 6. And in either case, there are the 6 ways to get that six-sided die to go, and there are 2 ways to get the coin to go, and that's a total of 12 ways. So if we use the fundamental counting principle to do a couple things, how many possible outcomes are there in the sample space? You spin a spinner with the numbers 1 through 5 on it and roll a six-sided die. Well, a spinner with 1 through 5 has 5 different outcomes, and a six-sided die has 6. And that's going to be 30 possibilities. And you can actually think about that. On your spinner, you can get 1, 2, 3, 4, 5, and then you can get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4. The problem is we'll be here forever if we do it that way. So we want to use this shortcut, the fundamental counting principle. A stack of cards contains the 13 clubs from a standard deck of cards. You pick a random card from the stack and flip 2 coins. Well, this stack has only 13 cards, the clubs, times 2 ways to flip the coin once, and then times 2 ways to flip the coin again. 13 for cards, 2 for heads or tails, 2 for heads or tails. So your sample space would look something like, well, there is no one card, isn't there? Ace, tails, tails, ace, tails, heads, ace, heads, tails, ace, heads, heads, 2 tails, tails, 2 tails, and I mean, we'll be here all night. It will be good evening to all of you if I just try to do this all day. So we would much rather say 13 times 2 times 2. 13 for the different cards, 2 ways to get the first heads or tails, and then 2 ways to get the second heads or tails. And that's going to be 52 possibilities. And what this really is this is a shortcut in order to find the probability of compound events. So the probability of the complement of an event, the probability of the complement of event A is 1 minus the probability of A. What that's saying is if there is a 32% chance of, I don't know, a squid in your locker, like when you go to your locker today, there's a 32% chance that I put a squid in it, which seems awfully high, then that means there is 100% minus the 32%, which equals 68% chance of no squids in your locker, the opposite. As long as those events are mutually exclusive, that one thing means not the other. Okay, finding the probability of a complementive event. When 2 six-sided dice are rolled, there are 36 possible outcomes, right? Because there are 6 ways to roll the first die and 6 ways to roll the second. Find the probability that the sum is 5. Well, let's see all the ones where the sum is 5. 2, 3, 4, 1 and 4. That would give me 5. 2 and 3 would give me 5. 3 and 2 would give me 5. 4 and 1 would give me 5. Well, that's kind of a fun pattern. I don't believe there's anything else, which means there's 1, 2, 3, 4 out of the 36 ways. which reduces to 2 out of 18, which is 1/9. Ooh, that's nice. 1/9 if you reduce that by 4, which equals 0.1 repeating, which equals 11.1 repeating percent. So find the probability that the sum is not 5. Well, that would just be 1 minus 0.1 repeating, which I do in my calculator is 1 minus 0.111111111, and I just type ones until I get bored, which is 0.8 repeating. Which is, by the way, as a fraction, 8/9, and that is 88.8 repeating percent. So we get a much better chance of getting something that's not going to add up to 5. Find the probability that the sum is less than or equal to 5. So that's going to be true of all these too. Get a different color out here because these summed up will be 4, 4, 4, 3, 3, 2, which means this whole block here is what I'm interested in. I regret making those decisions. Okay, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's a 10 out of 36 chance of getting something that the sum is less than or equal to 5, which reduces to 5 over 18, which is a decimal, 5 over 18. That's 0.27 repeating percent. Oops, excuse me, 0.27 repeating, which is equal to 27.7 repeating percent. Notice how your chances went way up. Find the probability that the sum is greater than 5 is the complement. That's the opposite. That's what's the probability that all this might happen, which you can see is better. But you do 1 minus 0.27 repeating, which again, I just do 1 minus 0.27777777777 till I get kind of bored. And then I take that away from 1 and I get 0.72 repeating. Which, as a fraction, well, as a fraction is just 1 minus 5/18, and that's going to be 8, 5, 4, 3, 13/15, 13/18, excuse me, which is equal to 72.2 repeating percent. And that's the idea there. Experimental probability, the probability of the events that happen in an experiment. Experimental probability is different from theoretical probability in that you actually do the experiment and your outcomes might be different than what you theoretically happen. If you flip a coin 10 times, you get 8 heads 8 of the 10 times. Experimentally, the probability of getting heads was 8 out of 10, which is 4 out of 5. Theoretically, it's supposed to be 1 out of 2. And I mean, that makes sense. If you flip a coin 100 times, do you think you are definitely going to get 50 heads and 50 tails for sure? No, you're probably going to wind up getting something like 55 heads and like 45 tails or something that's not exactly 50-50. But the further off you are, like if you flip a coin 100 times and you only get 10 heads, then you might start to think that something's up with that coin. So I guess the question is, how many times do you need to flip a coin before you start saying something is awry, which is one of my favorite words. I'm going to write that word down because it doesn't get used enough. Try to use awry in a sentence today. It means wrong or seemingly wrong. Finding experimental probability. The section of the spinners are numbered 1 through 12. Each section of the spinner has the same area. You spin the spinner 180 times. This table shows the results. For which number is the experimental probability of stopping on the number the same as the theoretical? So theoretically, the probability of each one should be 1 out of 12, right? Because if there's the same area, that probability, you should have it just as good a chance of getting any of them. So if I spin it 180 times, well, what's 180 times 1 over 12? Well, that's the same thing as 180 divided by 12. That is, this multiplied by the probability should give me the expected value. So you can do 180 times 12, 180 divided by 12, good job, Mr. P, 15. So you should expect to get 15, which is only this one that I can see, 9. because you got 15 nines out of the 180 spins. That's the only one that reduces to 112. And so 9 is the only result that matches theoretical probability. And again, if you actually look at this box as a result, as a whole, it's actually worth talking about. Do any of these results seem unusual? Like, do you think it's weird you only got 8 6s, or does that sound within the realm of possibility? How about 22 3s? Those are questions you have to ask yourself, because that's not part of what we're doing in this class this year, but I think I'd like to bring it up anyway. Solving a real-life problem. A manufacturer tests 900 dishwashers and finds that 24 are defective. Find the probability the dishwasher chosen at random has a defect. An apartment building orders 40 of the dishwashers. Predict the number of dishwashers in that apartment that are defective. So there's a 24, and see, this is why we wanted to not necessarily call this a desirable outcome, because there's 24 things we're trying to measure defective dishwashers out of the 900, which really seems like an awful lot. And I believe those are both divisible by, I want to say 6 at least, maybe even more. So 24 divided by 6, oh, that's 4. 900 divided by 6 is 150. That is divisible, and if I'm not mistaken, I can actually divide those by 4. Yes? Oh, no, I can't. I'm going to have to just reduce that by 2, which gives me 2 over 75. So 2 out of 75, because 150 divided by 2 is 75, right? Let's make sure. Yeah. 2 out of 75 dishwashers are defective. So if you order 40 dishwashers and your probability of getting a defective one is 2/75, that's going to be equal to, well, I'm going to do 2 over 75. I'm going to multiply that by 40, and you get 1.06 repeating. So you can't have 1.06 repeating defective dishwashers. So I would probably say that I would expect to see 1 or 2. But since 1.06 repeating is closer, I would say but closer to, but probably 1. Probably 1 defective one. So just make sure you buy that extra insurance there. I think that's it. Well, there you go, folks. There's a little bit about probability. I hope you learned a whole bunch. If you have any questions, send a message to your instructor. This is Mr. P signing off, and I hope you have a fantabulous and wonderful rest of your day.